the low frequency output resistance R naught. So this is what we are going to be finding in kilo ohms for the amplifier shown at 27 degrees Celsius with an RD, RS, RG. We are also to use R over L, ID, VTN, and RKN. And also we're given a lambda here. So using all of this, we are going to have to solve for this problem. Well, we are going to need to identify what type this is, what type of amplifier. And we can do this by looking at the notes linked in the description below the like button on page 143. We have our single transistor MOS amplifiers, and this looks like the one that's in the middle. So we're using the common gate amplifier. We can scroll down and it'll be on page 148 where we have our common gain amplifier and all the equations that we need for it. This is where we're going to be finding the RI and R naught shortcut equations. We are looking for our R naught. So we're going to be using this one right here. With this, we can start solving. So writing this out, we first have that our R naught is equal to, and since we have resistors and impedances in parallel, we have 1 over our RD. We're given our RD, so that's good, plus, and then inside of here, we are going to have 1 over our R naught. Now, we do not know what our R naught is. We need to find it. And to find our R naught, we can look at this page again. And below here, we are given some information. We've been previously told that R naught is equal to infinity. However, that's not going to really work for this right here. We're not going to want to use that. That's for only when we looked at something like this, where we set our R naught equal to infinity when we have our RD over R naught. It's important not to get those mixed up, otherwise there could be some wrong answers here. So looking at this one, we need to find R naught. So to find our R naught and our GM, we're going to look at page 92, and in page 92 we have this equation right here. So we need to use it. What we're going to end up using is this one right here, since we have all of the correct values. We're going to want to set our GM equal to the square root of 2 times the K apostrophe times our W over L times our ID. So we're going to have, for this problem, 2 times, or the square root of 2 times 10, or 100 times 10 to the negative 6 times our W over L, which is 82, and this is being multiplied by our ID, and the ID is 272 times 10 to the negative 6th. So with all of this, we can plug it into a calculator, and we're going to get a G of M of approximately 2.11, and this is going to be our G of M, again, 2.11. Now we need to find our R naught. So our R naught is going to be equal to, we have this down here, and what we're going to do is set it equal to 1 over our lambda times our ID, because we are given our lambda and our ID. So we're going to take these, plug it in together, and then we get about 735,295. So this is going to be the answer here, and then we can take this and plug it into our equation. So plugging this in for here, we are going to have our R naught be 735,295, and then we are going to have a 1 plus our GM, which is 2.11. Everything else is going to be 0, so GMB and GDS are 0, and this is because we're neglecting the channel length modulation and body effect. So with those 0, we can multiply this by our RS as well. So we're going to take all this, plug it in, and we are going to get for our answer approximately 27.198. And this is going to be in kilo ohms, and this is how we would go about looking at this problem and anything like it.